please support me through PayPal to devinwyndham@gmail.com. I also tutor both in person and online. I'm based out of Fairfax, Virginia. If you're interested in tutoring, you can also reach me at this email. All right, today I want to do a calculus problem on acceleration and velocity. The position function s of a particle moving along a straight line at t seconds is described by s of t equals 5t squared over 10 plus t squared, where t is between 0 and 10 inclusive. A. Determine the acceleration after 3 seconds. Okay, pause the video and try it on your own. All right, let's do it. First, note that I wrote s as a cursive small s, because if I wrote a print s, it might be confused with a 5. Let's say this 5. See how an s could look like a 5? All right, so I recommend writing a cursive s. In case you don't know how to write a cursive s, I'm going to teach you now. So, we'll first note that it just looks sort of like a triangle with a little, tail on the bottom or something. So let me do a bigger version. So here's a bigger version of a lowercase cursive s. Here it is in dotted lines with an arrow showing the path to make it. So I'm going to trace over it. All right, you might be wondering why the system of cursive chose to make this symbol be an S. I mean, it looks like a triangle, sort of. So let's investigate why this would be, an S. So at the top here, sometimes it's hard to see, but there's a little loop. When some people write it, there's more of a loop. So here's how some people might even write it. This is a bit exaggerated, but see this little loop at the top? Here it is again with even more of a loop. And now I think you can see an S. Can you see an S in here like this? So here's, this S. So that's why that's a cursive S. So, but it sort of degenerates into this. The top loop gets lost. It looks sort of just like a triangle. So that's this. This is S. Now, why is S used for frequently a position function? Well, I think of S as being the first letter of the word space. So I think of it as the particle's position in space. All right. So determine the acceleration after 3 seconds. So let's go ahead and take the derivative. I'm using Leibniz's notation. I find that useful. So we're finding ds dt, the derivative of s with respect to t. And we're going to use the quotient rule. I learned this little mnemonic for the quotient rule. Low, meaning low, the downstairs, the denominator. D high, meaning the derivative of the upstairs, which is 10t, minus high, so minus the numerator. D low, the derivative of the denominator, which is 2t, over the square of what's below. It rhymes. So over the square of the denominator. So let me see the mnemonic faster. Low d high minus high d low over the square of what's below. All right. What do I do to go from here to here? What did I do? It looks like I used the distributive law here, right? So we're using the distributive law. 10 times 10t is 100t. T squared times 10t is 10t cubed. Oh, and here I multiply, right? And I get negative 10t cubed. Excuse me. I'm going to just copy the denominator. All right, how do I go from here to here? I cancel the last 2 terms in the numerator. All right. The next line, I'm going to put a comma. Commas are like periods in math. We don't maybe put a period because it might look like a multiplication symbol. So here we have our acceleration, which is the derivative of velocity. Remember, velocity is the derivative of s, so this is velocity. And if we take the second derivative of s, we have velocity, if we take the second derivative of s, we have acceleration, because acceleration is the derivative of velocity. Now this notation here, this is a bar, the vertical bar, it shouldn't really touch the fraction bar. I meant to leave a space there. It means evaluated at. So I'm evaluating this at t equals 3, and it should be vertical perfectly, not slanting like I did it. All right, so again, we'll use this little mnemonic. Low, d high, minus high, d low, and for d low I'm using the chain rule, right? This is I'm consider this as a composite function, so I bring down the 2, I copy what's inside the parentheses, 10 plus t squared, I subtract 1 from the exponent, or the exponent. You can say either exponent or exponent. I'll say exponent. So this is a 1 exponent. You don't need to write a 1 exponent. And then by the chain rule, we have to multiply by the derivative of what's inside here, which is 2t. All right. And then I'm going to divide by the square of what's below. So we're dividing by 10 plus t squared to the 4th power. And you don't have to write the t equals. So I can just write this vertical bar in 3 to mean we're going to evaluate this at time t equals 3 because the question says determine the acceleration after 3 seconds. All right. Now, how do I go from here to here? Well, I noticed that the numerator and denominator share a common factor of 10 plus t squared to the 1st power. So I'm just going to factor that out of the numerator and then cancel them. So this, instead of having an exponent 2, now just has an exponent of 1. I'm just copying the 100. I copy the minus sign. I copy the 100t. This 2 marries this 2 to become a 4, and then this, just drops out because remember we're basically canceling the 10 plus t squared. This t is this t. This first t, by the way, I think I mentioned it was this t. The 2's again got married and became the 4. And then this 4 becomes a 3 because again we're canceling 10 plus t squared. And that's equal to, so we're evaluating it at 3, so 10 plus 3 squared is 19, and 19 times 100 is 1900, minus 4 times 100 is 400, and 3 times 3 is 9. 10 plus 3 squared is 19, so we have 19 cubed down here. All right. So in the numerator, I'm factoring out a 100. So we have, by the distributive law, the numerator is equal to 100 times 19 minus 36, because 4 times 9 is 36 over 19 cubed. Well, 19 minus 36 is negative 17, right? And with a calculator, that's approximately negative 0.248. So our final answer is approximately negative 0.248 units per second squared. Remember, the units of velocity are units of distance divided by the square of your time unit, and our time unit is at the second. They didn't give us the distance units, that's why I just put units. All right, B, when is the velocity greatest? All right, pause the video, try this on your own. Okay, let's do it together. All right, let's look at our velocity. Since the question is asking when is the velocity greatest, let's look at the velocity expression. So here is the velocity expression right here. Right here, this is the velocity expression. Notice that the denominator is always positive because t is between 0 and 10 inclusive, so this denominator is always positive. Let's look at the numerator. We're concerned about the sign of the numerator because we're going to look at its, because acceleration is the derivative of velocity, right? So we're concerned about the sign of this numerator. So the 100 matters not, right? Whether the numerator is positive or negative, I can factor out these 100s and just get rid of it. It's not really tampering with the sign. So let's just factor out this 100 and make it disappear. And so we have our simplified numerator is 10 plus t squared minus 4t squared, which is 10 minus 3t squared. Now this is a downwards opening parabola. And its vertex is at 0, 10. So clearly it's this parabola, it's decreasing. And let me do a little sketch of it, this parabola here. So it's like this. This is 10, right? And this point here, so this is half the parabola, right? The other half is here. What's this point? Well, this is, you know, if we equate this to 0, then this point has the x-coordinate root 10 over 3, right? All right, so acceleration is positive in this interval of time and negative in this interval of time. That means velocity is increasing in this interval of time and then decreasing in this interval of time. So this is at this time, at time equals root 10 over 3, velocity is at a maximum, so we're done. We have root 10 over 3 is approximately 1.826. So the answer is at root 10 over 3 seconds, or approximately 1.826 seconds. All right, I'll see you in another video.